Ladies and gentlemen, welcome to this webinar on bioenergy for flexibility in energy systems. We will be waiting for one more minute until we kick it off so everybody has the opportunity to join the room. So please be patient. Within a minute, we'll kick off the webinar. Okay, welcome everybody. Welcome to this webinar on bioenergy for flexibility in energy systems. My name is Christian Rakosch. I'm from the World Bioenergy Association, and we are organizing this webinar together with the IEA Bioenergy Agreement. The IEA is running a technology cooperation program on bioenergy since many years, where researchers around the world work together to bring the knowledge forward to develop the technologies to use bioenergy in a sustainable way. And we're very happy to have IEA together, IEA Bioenergy together, as a cooperation partner for this webinar today. Before I head over to our partner, let me just say a few words about the World Bioenergy Association. For those of you who don't know us yet, we are a global organization. We have a wide range of members. And what we are doing is basically we try to share knowledge on bioenergy markets, on policies, on technologies, on finance, because very often that is missing, that information is missing. And oops, can you please go back? Seems to be I'm out. Sorry for the glitch. Am I back? Yes. So we are sharing knowledge on a global scale, and we try to advance bioenergy use in this way. We also provide a platform to showcase your products, your services. We're publishing industry reports. We have a global bioenergy statistics report published every year that gives an overview on how important the role of bioenergy is. It is by far the largest source of renewable energy that humans are currently using. And we engage in partnerships with international organizations like the UNFCCC and others. So you're very welcome to join our community. We are steadily growing our membership base, and I must say this is really a very useful forum to stay in context, to learn from each other, and you're really welcome to do that. So with that being said, I will now hand over to our partner, to Daniela Tren. She is the leader of IEA Bioenergy Task 44, and she will give us a little bit of an introduction and why bioenergy is important as an element of flexibility in energy systems. And as you will see today, we will mainly talk about electric energy, But that does not, of course, mean this is the only energy system where bioenergy adds flexibility. Bioenergy has also an important role to bring flexibility to heat markets, and there will be a second webinar later on this year where we'll address this question. So over to you, Daniela. Thank you very much for this joint project, and please go ahead with your introductory remarks.
Thank you very much, Christian. Also from my side, my name is Daniela Trehn. I work at the Helmholtz Center for Environmental Research in Leipzig, Germany, and I'm holding a professorship in bioenergy system at the Leipzig University. We would like to thank you very much to make this webinar happen. And as you already said, I'm currently the task leader of IEA Bioenergy Task 44, which is about flexible bioenergy and system integration. And I can also hopefully make you a bit more curious, because also we talk beyond electricity and power markets. However, ladies and gentlemen, I'm sitting here and sweating in Leipzig, which means climate change is ongoing. And we have at least 10 years or even less to maintain our world in a well below 2 degrees system. And the good news is energy systems are in transition in many regions of the world. And transition also means that variable renewable resources like wind and solar are of increasing relevance. And, what we did from IEA Bioenergy Task 44 was a questionnaire and interviews with many different countries. You see them on the left-hand side, and some we talk about 15 expert interviews and questionnaires. And what you can see here is in blue that many countries, Europe, but also beyond Europe, like Turkey, US, Australia, Canada, are in a transition phase. And you see 6 phases given here. Phase 1 is, we don't need any system integration. And from phase 3 on, what's here, we have more and more varying renewable energy sources in the system. This means investment in flexibility, and then it goes even in requirement of advanced technologies. Here we talk about varying renewable surplus from days to weeks. And then the final stages, that's also about seasonal and interannual surpluses. And you see that, most of the countries did already investing in flexibility or expect. The green bars mean we expect this phase for 2030 latestly in this flexibility, and also expect to go further ahead, meaning requiring advanced technologies to ensure the reliability. So flexibility needs in power markets are, in a way already happening, but with regard to the, let's say, flexibility potential of bioenergy, we see even more options. And this means, first of all, flexibility is needed also on the resource base, because we need sustainable resources to feed this bioenergy, flexible bioenergy systems in the future. We have this, let's say, interesting interaction between variable or fluctuating power, wind and solar on the one hand side, and flexible power from bioenergy on the other side, what can support many energy applications. But we also talk about storable fuels for are these applications difficult to electrify, for example, transport or shipping, or also high temperature industry heat. We talk about that it's possible to support implementation of hydrogen with flexible bioenergy, because there could be within a certain system different demands for electricity, which also means we could interact with hydrogen. Flexibility and bioenergy could support and facilitate carbon dioxide removal in the direction of using it for biofuels or biomolecules or long-time storage. And finally, all these, let's say, very dynamic, manifold options need smart embedding in the energy system, which mainly means networked information exchange and small control system. So in a way, this is, let's say, the larger picture. And to also address this larger picture coherently, we have defined flexible bioenergy in task 44 as the deployment of sustainable biomass to provide multiple services and benefits to the energy system under varying operating conditions and/or loads, contributing to energy security. And this is a broad, as I said, a broad definition. It very well covers those many aspects. However, this common understanding of flexibility in general and also flexible bioenergy is in energy expert groups still missing. So if we talk about flexibility in other communities, for example, wind power or hydro communities, they mean something different. And this means that many, let's say, interesting elements for this energy transition, like energy strategies, energy system modeling, energy planning, etc., do not consider flexible bioenergy options appropriate just because, let's say, the language is missing. The good news here is that IEA has started a joint action, intertechnical program working groups to define flexibility between the expert groups. This work has started in May, and the results are expected at beginning of next year, or let's say mid of next year. So this means also here we can expect to have, let's say, better understanding between actors. As I said, we don't talk about the future only. I've provided you this broad, let's say, definition of flexibility. And of course, there are already many good cases in a broad variety. I will not go into these cases. I just would like to encourage you to have a look at the Task 44 IEA Bioenergy website, where you find about, I think, 12 cases now. And those cases are real established cases, but also cases with a lot of discussion, and maybe which did not come into action, though they also include maybe lessons learned. But you can already see here, we talk about e-gas plant in Werle. We talk about the lignocellulosic bioethanol plant in Australia, and the idea in Sweden with liquid winds, which is currently in a bit more difficult status. So options are there. It's important to, let's say, share, discuss, and exchange on these options. And this is why we are really happy to have also here today the practitioners who show us their approaches and experiences. Then, of course, it's also necessary to have policy and markers appropriate designed to make access for flexible bioenergy easy. And what we saw also in our questionnaires is that more and more countries establish direct and indirect support. Just give you some examples here: Denmark, Italy, Austria, Switzerland, Germany, the Netherlands, but there are more. The level of support is different, which also means the effect. It's different, but it is clearly stated that synergies with hydrogen and carbon dioxide removals are seen as potential accelerators. Why is it pointed out so clearly? Because hydrogen, but also carbon dioxide removal, like Becker's or biochar, have very strong dynamics at the moment, and here with bioenergy you can also find solutions which are not, or which are comparable, competitive. So these are important elements for the future support schemes, not only to look at bioenergy or flexible bioenergy, but also how to develop those synergies. We also ask in this questionnaire which issues affect the implementation of flexible bioenergy most. And there came out that there are 4 larger fields which could affect positively or negatively. And as more greener responses you see, as more positive effects are expected. Yellow is the no effect expectation, and blue is the negative effect expectation. The strongest effect on implementation of flexible bioenergy positively is expected from energy security requirements, and also from high energy prices. While high energy prices might bring a lot of problems in the energy transition, might be also, let's say, not many a development with many aspects, which is more difficult. Energy security requirements are, of course, an important issue for robust and resilient future energy systems, and here support not only is important for bioenergy, but also beyond. We see that also some positive aspects are expected from sustainability requirement, and of course high biomass prices are really kind of a hurdle. So with this, I would like to sum up what we from Task 44 see as the way forward. First of all, we need agreements on definition. I said here we are on the way with these ongoing joint activities at IEA. We need multiplication of best cases and lessons learned. This is also necessary to develop technologies and automation. I did not go into this topic here because the next speaker, Tilman Schildhauer, will talk about this explicitly. We need policy and markets addressing energy security. And finally, all these things are important for our today's policy to improve the implementation into the market. But with regard to our overall target coming into net zero energy systems as soon as possible, all these aspects also need appropriate consideration in long-term energy system planning to develop the options and optimize the options for flexible bioenergy, also with a strategic view. With this, I would like to thank you, and I'm happy to answer your questions. We don't hear you yet, Christian.
Sorry about it. I should have mentioned in the beginning that first of all, this webinar is being recorded and it will be available online on the WBA website. So you're happy to share the link and to have another view of this. Now, with respect to questions, I should mention that please, if you have any questions, put them into the chat and I will ask these questions. And there has been already a first question here that I would like to read out to you, Daniela, and that is, can flexible bioenergy bioelectricity really compensate for intermittent electricity supply, because the capex is high for bioenergy systems, and in view of high capex, these plants need to run for a long time. So can they really supply peak load? What would you answer to that question?
Yeah, thank you very much. It is a good question, and of course, capex is high, and I think it clearly depends on the frame condition. So one discussion which are ongoing in certain countries, if you for example develop capacity markets. Then it could be an option. It could be an option for regulatory electricity, and it could be interesting when building virtual power plants, meaning to have variable and energy providers, like for example wind and bioenergy, for example biogas, together in a portfolio, and agree on, let's say, rules how this demand is answered. And if you have this virtual power plant, then you could contribute to the electricity market. So I agree with you. You really need some additional, let's say, concept or political frame condition that it works.
Right, right. Thank you. Thank you, Daniela. And that takes us to our next presenter. It's Tilman Schildauer. He's senior scientist at the Paul Scherrer Institute in Switzerland, and he will give us an overview of technical solutions for flexible bioenergy. Tilman, the floor is yours.
Okay, yeah. Thank you for the introduction, Christian. So my name is Tilman Schildauer. I'm actually also a member of the Task 44 of IEA Bioenergy. I'm there the Swiss representative, and when I'm not doing that, I'm actually a senior scientist at Paul Scherrer Institute, which is the national lab of Switzerland, and there I'm responsible for the research in methanation and all power-to-X processes. Now today, I will show a little bit how flexible bioenergy can actually support the transition in the renewable energy system, and I would like to go a little bit more into detail. And for that, I start with the overview. So actually, we have challenges in our energy system, and these are the main four ones. So we have this intraday mismatch of electricity supply and demand. So that was actually also what was one of the questions. We definitely have a seasonal and sometimes also regional mismatch of energy supply. We have to defossilize all sectors, not only electricity. So there is actually heating of buildings, industrial heat, so high temperature heat, and then all kind of transport, fuels, aviation, very difficult, but also actually the feedstock for the chemical industry should be not fossil anymore, what actually largely is today. And finally, even if you have done all that, there will be some need to compensate unavoidable CO2 emissions or methane emissions from agriculture. So we need to do some sequestration of carbon, either as carbon or as CO2. I mean, the very first thing what you can do is you can start to be more efficient on all sectors. We could also always look into demand side management. So that would be, let's say, not so much technical, but more behavioral starting points. But there's also a lot of technical solutions already there, which actually don't need biomass so far. If you look into the intraday market, then it's pumped storage hydroelectricity, very important topic for Switzerland, which makes our life a little bit easier. Unfortunately, not available for all countries, or batteries, especially batteries on small scale close to your PV plants. If you think about seasonal or regional mismatch of energy supply, there's not so much so far. The main thing is reservoirs, so actually dams where we actually keep water from summer to winter, usually, or to the late spring, when we still have a lot of electricity demand. And if you think about the defossilization, then there's especially heat pumps, so which take away the need to burn something to get heat in buildings, especially this low temperature heat, which we need in space heating. You can do district heating with heat sources, which you have anyway, like waste incineration, and we can electrify cars, trucks, and also at least some of the processes in industry. And if you think about negative emissions, then we can think about direct air capture of CO2 and then storage into geological site. So all that is without biomass. So the question is now, what about biomass? What can biomass do? And the answer is actually biomass is our joker, is our wildcard. We actually can use it for all of these options or these challenges, and I will show examples for that. And we can actually decide when we do it and where we do it. So this is one of the messages I would like to convey here is there is not one fit all. Actually, it might depend actually on the boundary condition, on the already existing infrastructure, which solution you finally choose. So if you start with the first one, intraday mismatch of electricity supply and demand, then it's fully clear we have these biomass plants which actually are able to deliver electricity on demand. So we start on the left side, we have the feedstocks. Here we mainly distinguish between dry biomass, so woody type of biomass or lignocellulosic straw, things you can somehow store for some while without them decaying. And we have wet biomass like digestate or manure, leftovers from food industry, things you would not like to store too long because they start decaying relatively fast. And from these we get actually intermediates with standard processes. So from the wet biomass we go into digestion, so anaerobic digestion. We get biogas from lignocellulosic biomass. We can go via gasification to product gas or to pyrolysis oil by fast pyrolysis, or we can use the biomass right away as pellets and chips, which are actually quite storable, and then go into combined heat and power plants. And here it's quite interesting that clearly they can produce electricity, and we should then use them more on demand than it's now. So we need some flexibility, usually because the electricity production comes with heat production. So here it's important to have actually a heat storage, which actually allows to decouple the moment where I produce electricity and the moment where I use the heat. Because usually, often these days, CHPs are operated based on the heat need, but by heat storage, we can actually decouple that. And here, the photograph on the right-hand side in Linköping in Sweden, it shows a hot water tank, which actually allows to do that in a district heating system. If you think about the devices, especially ones which are operated with biogas or pyrolysis oil, it could be internal combustion engines or steam turbines, organic rankine cycles. They can ramp up and down relatively fast. So this is within minutes, and very often they can actually go from 0 to 100% in the time range. So they give a high flexibility and are perfectly technically able to cover, let's say, the gaps which are somehow left over from PV and wind. If you think about processes which contain a combustion or gasification step, then usually the startup is several hours, and you usually don't want to stop it completely, but also these allow some flexibility in the load. If we go to the second mismatch, this is the seasonal one, and then here what we have to do is actually we have to take these intermediates, which I already mentioned, so the biogas, the product gas, the pyrolysis oil, and we have to go into energy carriers, which are kind of standardized and for which exists a working storage and distribution infrastructure. So typically would be methane or also LNG. Pyrolysis oil, for example, can be stored several weeks. I even heard about months. But if you hydrotreat it, then it's more or less you can store it for years without any changes. Pellets and chips I already mentioned that they can be stored. I mean, this is the most traditional way how we store energy from summer to winter. We take wood and use it in winter, right? This is what we know already since a long time. And what clearly is coming up is hydrogen. Strongly depends on whether there's a hydrogen infrastructure, both for the distribution and the storage. And that already shows these things can be very different from region to region. So if there's no hydrogen infrastructure, you cannot store it, you cannot distribute it. If you don't have a methane grid, you cannot do that. Energy transport without harbors is also not easy. So you see, by this infrastructure which is needed here, there comes actually this regional differentiation into the picture. And here for the color code, you see 3 different colors. So green are things which are already applied in a large amount. We have yellow processes. These are those which have been demonstrated in a technical way, but the business cases are only starting now, so it's not completely there. And then red ones are things which are still under development, like the hydrogen. If you look into that, then we see that there's actually, if you produce from product gas or biogas, energy carriers like hydrogen, methane, LNG, actually the energy carriers don't contain oxygen, but the intermediates do, so we have to take out CO2. So we have a very cheap CO2 source because it's already part of the existing processes or business cases to separate biogenic CO2. And that actually is a perfect moment to combine this biogenic CO2 with hydrogen in Power-to-X processes, which actually allows you to take the CO2, take the hydrogen from renewable electricity and produce more of your product, of the energy carrier. And this is actually quite interesting for energy systems, because if you think about relying our electricity supply on wind and PV mainly, then we know that at certain times and also certain regions, we will have more electricity production than we can need at these places. Sometimes it's just too much, sometimes it's just a problem also of the electricity transport. So in that cases, you can only curtail, or we could use this electricity to produce hydrogen, either use the hydrogen right away, or if we need to put the hydrogen into some infrastructure like the methane grid, then we can do actually this power-to-X or power-to-gas processes. And in our eyes, because the CO2 is already there and it's relatively easy to combine these 2 processes, has been shown in long duration tests and also scaled up, like this gas plant in Welte, that actually could be an enabler to improve the economic feasibility of large overcapacities of renewable electricity supply. So we think this is an important piece of puzzle to make this market working. But it means we also have to do it in a flexible way, so we can use the hydrogen only when there's enough electricity and we don't have to save on electricity. So largely said, this is something we should do in summer, but maybe not in winter. Then if you speak about defossilization of all sectors, then it clearly needs, we also need liquid fuels. So that could be diesel type of things, aviation fuels, but it could also be just methanol, a starting point for all kinds of chemicals. Also, these can be produced from biomass, actually more or less from all of these biomass sources. Still, most of the processes are still in development. This beautiful plant is the very first one in this large scale, which really produces a transport fuel from biomass all the way down. And then the last thing which we would like to talk about was this negative emissions. Can we use biomass for negative emissions? And there are actually 4 options to do that. And the very important one, which usually gets forgotten, is actually we should have more wooden buildings. Actually, if we use wood for buildings and the building is standing long enough, that's a clearly storage of CO2, which was taken from the atmosphere. And on top, we also save on concrete and bricks and steel structure, which actually are usually quite energy intensive. So we have here a double effect. So this is from all the system models. If you really do that, wooden buildings are the best way of doing that, and then there's still enough waste left over to do all of the other process which we're talking about. So then we can take also CO2 from the processes. Let's say in winter when we don't have too much electricity, you anyway have to separate the CO2. It's process inherent to get this energy carrier. So if that is stored in a geological site, then it's a negative emission. Then something which you can do is you can actually produce biocoal or biochar by pyrolysis type of processes. Then you can actually store the this biochar so there's actually the idea to put it into fields, especially to improve also the soil. Then it would be a negative emission. And on the final point, if a kind of more or less centralized use of these biogenic energy carriers, like in CHPs or so, then I even could actually equip that plant with the CO2 capture. And again, if I have the infrastructure, use the CO2 for negative emissions. So we have really a broad way of combining all these things. And that leads me to my last slide, and the last slide still contains quite some messages. So I hope I could show you that flexible biomass is really a valuable wild card, because you can really do many things, and often you can choose also when you do it. We can cover peak demand, seasonal storage, and also negative emissions. All that is possible. And what I would really like to stress is, especially this power to X with biogenic CO2 or biogenic carbon, could really be an important support to having large capacities of PV and wind. So if you come above 50–60% of electricity production by renewables, then you run into all kinds of problems, and biomass could here really be a completely complementary player. What is really important is if you think about market regulations and incentives which are needed, in my eyes, we should make sure that there's no preference for certain technologies, energy carriers, or services, because many of the technologies are still under development. You have seen the colors were changing, red, green, and red, and yellow. So if the regulations are too strict, we might cut away complete technology branches, which maybe is a disadvantage in the overall system. And to decide what we really need, we have actually make sure that these technologies are all represented correctly in the systems model. As already Daniela said, we have an issue here. People don't have that correctly in their model, and then no surprise that the model does not predict that biomass can solve a problem or can be part of the solution. So this is really important work that we better represent these technologies in these models. And then the final remark, which I already mentioned before, really have different solutions from area to area and region to region. I'm coming from Central Europe. When I was talking to the Nordic people from Scandinavia, I learned a lot, because their heat has a completely different value than it's here in the more, let's say, warmer region of the continent. This is only within Europe, you already have large differences. And if you think about this is a World Biomass Association, different continents, again, have completely different needs. So we should not try to find one recipe which works everywhere, but we should carefully think, because biomass is expensive and it's usually also not too much available. And if it is available, it's available in a decentralized way, and it really needs that we think carefully what we should do. And if there are easier ways to fulfill a service, like using heat pumps, we might use a heat pump for domestic heating and then save the wood for something which is more difficult to do. And we strongly depend there on the infrastructure. Are the district heating grids? Is there a gas grid? Is the gas grid then containing hydrogen or methane? All these type of things we have to think, again, together with the logistics of the biomass. So logistics in Switzerland is very difficult for biomass, because there's always a mountain in the way. The same in Finland is way easier, because it's easier to transport wood, and there's actually also more accept. So that would be my input here, and I would like to finish with with the same advertisement which Daniela did. We actually in Task 44 did a lot of work on that. There's a very nice report. We are working it over, but it already exists. It's about 20 pages generally, and then for all the technologies, there's a technical appendix. So the whole thing is close to 100 pages. And we have this very nice best practice example homepage here. So we have example from Germany, Finland, Sweden, Austria, Switzerland, Australia, and so on. And actually, here in the lower right corner, you see this very nice wood-based biochar producing CHP, which actually contains a Synkraft gasifier. So it's even maybe a nice starting point for the next speaker. So thank you very much for your attention.
Thank you so much. Thank you so much. That was very interesting, Tilman. I have two questions here I would like to put forward to you, and one you have partly already answered, and that is, there are so many possibilities to use the biomass. Is there enough biomass to do all of this? And I guess the answer is, we're not proposing to do everything everywhere, but we will do things that are useful in one place, and we do things with biomass that are useful in another place, depending on the local conditions. Would you agree with that?
Absolutely. I really would make a lot of advertisement, because people always think very roughly about these technologies, but we have to really look carefully. And even in Switzerland, which is a small country, in the one valley, you might choose a different solution than in the other valley. Always think about biomass is scarce. So maybe, okay, maybe Finland looks a little bit differently at that, but in most European countries, we don't have so much biomass. It usually can cover maybe 10% of the energy demand. We have to think very carefully what we do with this 10% and use it in the best way, very flexible, to make the overall energy system very resilient. So that is really something we have to think of.
In the best way, and also in the most economic way, obviously, because if it's not economic, it's not sustainable in a way, right?
Which brings us back to the regulation case, because often it's about regulation. The cheapest usually is what we do so far, which is not sustainable.
Well, this is a really tricky question, isn't it? Because, I mean, regulation has a profound impact on what is economic and what is not. And if the regulatory policies are very smart, that's the ideal case. They will put the bioenergy where it creates the most value and makes the best kind of contribution to stabilizing our energy system. But it's not obvious which one it is, because is it more important to fly airplanes, or is it more important to heat your stove at home in the winter time? These are questions that are not easily answered. Anyways, there is a second question I'd like to put forward to you, and that is, oh yeah, well, biomass actually contains carbon, so doesn't it contribute to CO2 emissions, Tilman? A short answer to that question, which is very often put forward.
Yeah, so there's actually two aspects here. Actually, on the pure carbon balance, it's more or less neutral, because the plants, all the carbon which you find in plants, have been taken from atmosphere before. In that respect, it's a kind of neutral. If you think about that, we transport the biomass, that maybe if you think about food residues, there was fertilizer used in the production of the biomass. There's electricity involved in some of the plants. So then we know it's not completely zero, but it is still a very low greenhouse gas potential in using biomass. So if you think about only the carbon, then it's completely neutral. Then if you think about also the processing and transport and so on of the biomass, then we have there's some footprint which you have to keep an eye on. But the more these become renewable and sustainable, the better it is in the overall balance for the biomass use.
I would put one caveat to what you have said, Tilman, and that is, of course, assuming that the biomass has been produced in a sustainable way, which is unfortunately not the case everywhere. Like, there are parts of the world, particularly, for example, in Africa and South America, to partly also in Southeast Asia, where the amount of biomass that is taken out of the system is higher than the amount of biomass that is growing. Particularly, for example, in Africa, we have really big-scale deforestation, in some parts of South America also. And in that case, of course, you do have net CO2 emissions. So it's always the question of balancing growth and harvest. So with that, let's go to the next speaker. And the next speaker is Marcel Huber from Syncraft, and he will show us a fascinating example of how a renewable energy system can contribute to energy generation and CO2 sequestration at the same time. Marcel, the floor is yours.
Thanks, Christian. Can you hear me?
Absolutely.
Perfect. So I try to share my screen. Can you see the presentation mode or the wrong mode?
The wrong mode.
Okay, give me a second. Yeah, thanks for inviting me to present something which is again.
That's fine now. No, that was good.
That was good. Sorry, it was too quick. No, I think what Mr. Schildauer said is all I have to say in the next 12-15 minutes as well. So it's all about what we say, that the framework. Some words about what we're doing. We do plants, what we call reverse power plants, and they are somehow unique in the case that that they do something in a biorefinery atmosphere. A few words about us. We are an Austrian company. We are in our 15th year now. We are a university spin-off, and we have set our sails towards green energy, but also with a clear scope on negative emission, which we see key and essential for bioenergy of what we saw the second or third generation. What the heck is a reverse power plant? I mean, we all know what coal-fired power plants look like. They use carbon and provide electricity and provide a lot of CO2, which might cause a bit struggle at the moment. And actually, we're doing the whole thing in the reverse mode. And of course, there's the tree in between. So we are a wood-based system. So the wood, the tree is doing all the job, but what we provide is as an essential second or third product, depends how you put it. We produce green carbon by intention. And what we think is that this is one of the most crucial raw materials in future. When we talk about flexibility, and I think this is the most important slide I want to share and discuss with you today, is the flexibility which you can provide with a modern bioenergy system. So what we are building on our system on is on wood-based residues. So whenever you build wooden houses or go for blankets or go for raw materials like cellulosic, you have 2/3 of residues, which would decay within a year or even faster, depends on the boundary conditions. So these residues would be emitted to the atmosphere anyway. And the idea is to give them a good fate. And here comes bioenergy from my basic principles to valorize these residues. So the key idea is no tree is chopped for bioenergy in its main purpose. That's crucial. Then we have our system in the center, and we can provide different modes of operation. So that means our plant can provide, as it also produces green carbon, we can produce more carbon or more energy, respectively gas. So these are the two modes we can operate the plant, but you can't produce ash with our system. So it's always carbon in a different shape, in a different configuration, and the gas. And so we end up with a lot of options, like a box of opportunities, I would call it. And on the top, you see one that you might not expect, but the system we provide is primarily built to provide green gas for industry, which is a very clean, bit reduced in heating value, but it burns still above 1,000 degrees. And it can provide at a very cheap basis a replacement gas for natural gas or other gases in industry, far cheaper than hydrogen's expectations are. Nevertheless, it's not gridable. So we can't introduce it into the grid or make it methane-like because it would be too costly. But you can also use it, of course, in a classical traditional way, what we call combined heat and power, of course. And the sweet spot is that we can situate a hybrid that produces gas for industry, But at the same time, if the electricity prices are high enough, they can switch to a CHP mode. So this is a big advantage. You can handle with a one unit the different energy prices and markets to switch whatever makes it more suitable. And with this setup, you of course also have a very high flexibility and quick response on markets. Due to the fact of the quality of the gases we produce, we can apply gas storage devices, not in the same dimension compared to biogas plants, but based on a daily basis, we can put the 24 hours concentrated on 4 hours with only a little more investment, which is a big advantage. And of course, totally underestimated at the moment is that we turn a decayable raw material or energy carrier in a non-decayable green energy carrier, which is green carbon. So you can store carbon, from my perspective, forever when it comes to normal timescales. And you can use it from a replacement of a brown coal powder to get energy, to additives, to reduction materials in the steel industry or similar. So it is an incredible source of industrial applications what you have with the green carbon, not only in soil. So soil is of course also a great application field, but there's much more to do with the green carbon, and that allows a lot of things you can do with bioenergy systems that are built to run a 8,000-hour basis. So this is not done only for the cold season, but also for the rest of the year due to industrial applications. Just a few plants to give all the schematics some real life. One we have seen already, the big plant in Switzerland, but we also have plants in Austria, in Japan. All of them are on a decentralized size, 1 megawatt, 2 megawatts, maybe a half megawatt. So this is also a very decentralized baseload approach we follow. And we also have seasonal plants like the one which has become a CHP of the month in Germany recently for the Hansawerk Natur as a 1 megawatt plant that runs on forestal residues. An overview what we have done so far, it's only a drop towards negative emission or defossilization, but still it's not nothing. So a few numbers, we've built 43 plants so far, and we are quite proud to be an Austrian built power plant system. Quite crucial is also the technology which is behind. Some of you might be aware what we are doing, but it's very unique. So I want to share the insights with you as well. And I think this is crucial if you think about bioenergy, biorefining. You have to do these stepwise approaches. Otherwise, you end up with intermediate products that might not fulfill product level or whatever. So what we are doing in our system is that we do a classical pyrolysis, but we do not do it without air. We add some air to carbonize the fuel. So that is a very important homogeneous step that puts this unhomogeneous biomass into something more even, the biochar or biocoal. Then we add air in the second stage to burn all the dirt and the gases, the pyrolysis gases from this first stage, to turn them down into three elements. And the three elements are CO2, water vapor, and carbon. And with these three elements, we combine them together into our producer gas, which is very, very clean, and into clean carbon or carbon-rich biochar as the second product. And the gas then is sent to for example, an engine, but can be used for many other applications, except upgrading it to be introduced into the grid, at least, or as long the grid is defined by methane and such high heating values. So this is what the technology is about, and as said, that we have this very clean gas, and you might see the flame now, which is coming out directly after the filter, without any real gas treatment, and that is what it makes it so valuable, that you can more or less replace it wherever you need such a flame in industrial applications, or of course also in engines or turbines, whatever. When it comes to forest residues or the fuel, and these never-ending question about do we have enough biomass, it always comes along valorization of biomass, especially wood, for higher applications like building houses or making bioproducts, bioplastics, whatever. But there's a big share of fuel which is not suitable for that applications, and this is to valorize these shares on the best way. We've already heard what we call the bioenergy, the ultimate love story, which is biochar and carbon capture. From our perspective, both can be combined in plants. What we're doing, we are actually building, I don't know whether it's the first, but maybe it's one of them. So one of our plants is actually being retrofitted with a CCS unit. So it produces biochar and liquid CO2 on a single site. It's in Austria. And looking on the overall CO2 storage capacity, you see a normal plant from us is storing away roughly 30% of the inputs CO2, and 70% are re-emitted. So the 30% clearly account as negative emission or climate positive if based on sustainable fuel, for example, with RED 2 or RED 3, which our plants already apply for. And if you add then a CCS unit, you can go up to more than 80% on a very cost-efficient approach, which turns the plant into, from a bioenergy facility into a green materials supply facility. So you produce liquid CO2, in that case for the beverage industry, even if it's not the CCS, it's a CCU approach. But that's something you can start with on a local basis quite easily. Otherwise, if you go for big CCS plants, the big problem becomes the transportation. And that's also the big advantage when you look at the biochar. The S is not the issue. So this is the big advantage, and all the economics and comparison is quite equal between PEX and BCR. But the storage system becomes a very easy job if you think about biochar compared to liquid or gaseous CO2. What we offer, we build these plants ranging from a 5 gigawatt heat demand. So most of the plants are always developed from a heat perspective. It's perfectly combinable with heat pumps, boilers, whatever. So it's only one part of a big puzzle in our understanding. And we can also provide baseload heat units or daily sprinters when you think about electricity markets. So the big advantage, as said, with a normal biomass CHP plant, it might get a problem, but due to the fact that we are able to store out the gas, we can build more engines that with a baseload unit, and then you can really peak load for 4 hours quite quickly. Yeah, and the negative emission, I think, is the key for all future bioenergy plants. And that is also the necessity that negative CO2 plants have to run 24/7, 8,000 hours a year, because otherwise they do not generate the negative emission, and the negative emission fulfilling the Paris Agreement is an 800 gigaton job at the least. So it's not a small task. Yeah, that's it. And I think the job is big enough. So we have to, the whole energy systems, the whole renewable energy system have to do all their best to cope with the challenge we're all facing. Thanks for your attention and looking forward to the questions.
Thank you so much, Marcel. Amazing what you have been achieving in these 15 years, because really producing electricity from producer gas is not an easy task, and has been very often tried and very seldomly really successfully achieved on a continuous basis. So I think that is really a great achievement, what you have done. Can you give us a short overview in which countries are currently most interested in what you're doing?
Very good question. Actually, on a technical base, the key thing is that you have this heat demand on a annual basis. I would call it. So whenever there is a district heating tradition or understanding or policy framework, I think this is a perfect place for such units. But of course, also the electricity prices or the energy prices for gas have to match. So there is it's not only a single basis you can answer this question from. So the fuel is crucial, which is available in Central Europe or all over Europe, I would call it. If you think about fire prevention in the south and forest management to Central Europe and Northern Europe, for having a lot of residues, but without proper value and a policy framework that addresses the task for bioenergy, it's very flipping. If you for example take Germany, you have so many different views on the role for bioenergy in Germany, which is not set yet. We have a high possibility of providing flexibility and a negative emission, but it's not yet in any policy framework. So it's actually at the moment in Austria, boundary conditions are quite good, because we have the situation that we have a clear understanding that bioenergy, modern bioenergy, efficient bioenergy is part of our future energy supply. But this is often discussed in many countries at the moment, whether it's CO2 neutral or not, or whether it's part of the game or not. I think the more we will reach 2030, the clearer the picture will become that biomass is inevitable and crucial. But yeah.
So give us an idea, Marcel. Give us an idea. A 1 megawatt plant. What level of investment are we talking about? Approximately.
I could give you a clear scope. I think the 1 megawatt plant comes at a 5 million
euros.
Install the commissioned core scope, so not the housing and so on.
Yes.
And
yes.
I think the only thing that we are really doing different is the green carbon. So in our case, it comes on top of the revenue. Yes. So you do, we have a electric efficiency beside the carbon production of almost 30%. So this is key in this small scale. And we spare away some heat to get the biochar. So it's not something magic, but we put it on top. So it just adds a bit more fuel to get these mature clean carbon. And with this third value stream or additional value stream beside the gas, the economics are different. So you can invest more because, as Jean-Marc said, and so I mean, bioelectricity is not the cheapest way to produce electricity, and it takes a lot of time to run. So you have to have boundary condition and economic framework that allows you to run the plant at 8,000 hours, and our fleet is actually running on 90.1, I think, percent. So this is of course crucial. If you only operate it on 2,000 hours, it wouldn't work. Yeah.
Yes. And would you expect in the future that this third revenue stream will mainly come from carbon markets, or do you believe that it might rather come from utilizing the carbon that you're producing for whatever reason, as a fertilizer or as an input into chemical industry, or into producing e-fuels or stuff like that? What is your expectation?
I think it's in both ways. What I can share is that a big industry has already understood quite deeply that there is no way around green carbon. If you just think about steel or green steel, it's understood that you can't produce green steel without green carbon. So the hydrogen is making some part of the way, but it will become essential in very big volumes. And of course, this also contested in terms of price. But like all other renewable energy systems, or the CO2 issue as in general, if the ETS market and the prices for CO2 are not reaching high enough prices, it's always a big issue. So the key for the carbon market to really skyrocket, so to speak, is the CDR market, of course, on the one hand, so carbon dioxide removal, what is paid for an already reclaimed CO2 from the atmosphere, and for the emission avoidance market, the ETS, so the emission trade. Those two things will define BECCS and BCR's fate in the next years, but yeah.
Okay, thank you very much. And with this, we continue to our last speaker, Per Johansen. He is transformation expert at Siemens Energy, and he will talk about how flexible gas turbines can play a role in flexible making electricity supply more balanced, and what role biomass can play in this context. Please, Per, the floor is yours.
Thank you, Christian, and good morning, everybody. Thank you for this opportunity to give you a little bit of practical examples of what gas turbines can do in this context. And I'm Per Johansson. I'm working for Siemens Energy in the factory we have in Finspång, manufacturing gas turbines. Finspång is in Sweden, by the way. We're manufacturing industrial gas turbines and heat pumps. But we also have a team working with energy system design, which is where I belong. But today I have been asked to talk only about the gas turbines, and I will refer mainly to the gas turbines that we manufacture here in the factory in Finspång, which is between 25 and 60 megawatt. So I will share my screen, and let's see. Hope you, sorry. You'll be able to see it now. Sorry, I can't hear you, Christian.
The presentation mode, please.
Yeah.
Yes.
There we go. Yeah. So this short presentation will cover the introduction just to gas turbine applications. Maybe most of you are familiar with, but anyway, I think it's worth a quick introduction. How gas turbines can provide the grid balancing services that are more and more required in today's modern grids. And the most important question, how ready are the gas turbines to run on different kind of biofuels or different kind of fuels, and some short conclusions. So gas turbines, as most of you know, are used to convert chemical energy to mechanical energy. And the mechanical energy can then be used to drive different kind of equipment. And in this case, we're looking at that they're driving generators. In its most simple application, the gas turbine is converting only the fuel to electricity. And roughly, as you see here on the screen, the efficiency then, the fuel efficiency is between 35 and 40%. In many cases, you add a waste heat recovery unit behind the gas turbine to make use of the rest of the, more or less, the rest of the energy that is coming with exhaust gases. So with this setup, which we normally refer to as CHP, combined heat and power, you can reach up to efficiency levels even above 90%, actually. And if you want to maximize your energy, your electricity production with such a system, you can, from the exhaust gases, you can produce steam, and that steam you use to drive a steam turbine instead and produce more electricity. And then you typically can get up to efficiencies of 60%, slightly above 60% for really big installations. So this slide is very busy, but I hope I can take you through it. What we want to highlight here is that gas turbines is actually the Swiss Army knife when it comes to providing ancillary services for the more and more volatile grids over the globe. Gas turbines in operation are actually covering the whole spectra of required ancillary service, from providing inertia, from providing reactive power for voltage control, to secondary response, primary response, secondary response, and even for long-term power reserves, which is needed for the tertiary response. So what is important to take with you from this slide is that if the gas turbine shall provide the whole spectra of the required energy ancillary services that is asked for, the gas turbine is most flexible when it is in operation. So a gas turbine, typically, depending on size and model, needs from 2 minutes to, let's say, 15 minutes to start if it is in cold standby. And when it is in cold standby, it doesn't provide these, the first levels of ancillary services. So therefore, it's important to look for possibilities to keep the gas turbine in operation at a low operational cost, which is what I cover in the next slide. And this has already been discussed a little bit earlier by Tillman, for example, that if you have a heat off-taker making, let's say, it viable to have the gas turbine running, even if electricity is not demanded, then you can set up a combined heat and power system. And as I said in the first slide, you get up to 90 and even above 90% overall fuel efficiency. The problem here is, as we discussed, heat production is connected to power generation. So if you only need heat and not power, then it's not a very flexible solution. But as was discussed before, if you decouple the heat production from the power generation with a thermal storage, which for low thermal storages are a very low cost investment, I would say, then you can have a much more efficient and much more flexible power generation and grid support function of your gas turbine installation. So the increased capacity per heat demand makes smaller heat demands still economic for combined heat and power, because then you can operate your plant in this way. You can continuously provide your heat demand with a varying demand on electricity and meet the power demand only when there is a real, let's say, demand for the gas turbine or the plant, if it also includes a steam turbine, to produce electricity, when you decouple the power generation from the heat generation and store the energy, the heat in the storage. So then the most interesting question of this is this now possible to do with biofuels? And this slide shows an overview of the fuel flex, green fuel flex roadmap that we have for the gas turbine manufactured here in Finspång, Sweden. There are a number of similar roadmaps for our other models in the program, of course, and they are not 100% identical. Of course, some gas turbines are better in one area and worse in another area. Currently, we focus a lot on the gas phase capability, and of course, hydrogen is always, let's say, in focus, and also ammonia. And currently, we run our gas turbines with the dry low emission combustion system, meaning very low NOx emissions. We run them on 50% cracked ammonia and up to 75% hydrogen. We are looking at being capable of running on 100% in the very near term for 3 out of our 4 models. Whereas the liquid phase, I should mention, of course, biogas is normally, it has a very much varying composition, of course. Some of them are more or less identical with natural gas, and some are a little bit weaker due to more content of CO2. But I would say that typically all kinds of biogas are possible to use in our gas turbines without any problem. And we have references quite some years back on different kinds of biogases and different kind of what we name as weaker gases. When it comes to biodiesel, we have just recently proven that on liquid fuel biodiesels are 3 of our models are capable of operating continuously on biodiesel, and we are also targeting FAME, and in the long run we also look at methanol and ethanol. And the reason for methanol and ethanol being a little bit further away is more or less the market requirement for gas turbines to run on these kind of fuels. But depending on what happens on the market, methanol and ethanol could be pushed back and be developed a little bit earlier. It's not the most difficult thing to get the gas turbines verified on methanol and ethanol. So for some real references, since 2020, our test facility here in Finspång is operated on blends of biogas. So we are actually importing to the site as much biogas we can to be used in our testing facilities. Every gas turbine is tested before it's shipped out from the factory. And as you see here, we can operate on biogas compositions with the WBA index down to 22, 25. So maybe everyone is not familiar with the WBA index, but this corresponds typically to a heating value of 20 megajoule per kilo, for example. So we can go quite far down with our standard combustion system. We can also modify to go even further. Maybe not as low as Marcel's pyrolysis gas yet, but it's definitely not an impossible thing to redevelop the combustion system to be capable to run on those weak gases as well. One example we have on the biodiesel is that we have 3 units in Gothenburg that have been in operation on natural gas for 10-15 years. They are providing power and district heating to the local district heating network. In 2021, we verified this plant to be running on HVO 100 liquid diesel, and while still maintaining the capability to run on natural or to run on gaseous fuel, of course. So this is a dual fuel machine supporting the district heating network, the local grid, and is quite much already used for grid ancillary services actually now, due to the high efficiency of this setup. Another reference is Stockholm Exergi, where we in 2023 commissioned a backup gas turbine, 60 megawatt, for the Stockholm local grid, and it runs on 100% HVO 100 as well. So the capability for both gaseous fuels and liquid fuels from biogenic sources are, I would say, already there and has been there for quite some time. So the conclusions from this presentation and what I want you to bring with you is that gas turbines are actually the ideal technology for supporting stability of electrical grids. And this flexibility combined with the already developed and proven fuel flexibility is the ideal combination. However, for frequency regulations, spinning reserve, voltage control, and load following, as I was discussing, it requires the gas turbine is in operation and connected to the grid, and then cost of fuel will be critical for economic viability of having the capability to provide these services to the electrical grid. But a decoupled heat and power generation is providing a very good opportunity, a possibility to set up such a system and get economic viability in it. I should also say that a combination, if it's not viable to run continuously with the gas turbine to provide, let's say, these first levels of support, it can very well be combined with a conventional battery system. And that is analysis that we've been done in other projects, combining conventional battery systems with gas turbines. And the gas turbine is then in cold standby, but running on biofuels. So that concludes my presentation. If you want to have some more details compared to what I had the time to give you here, you can download this report from us, which you will have in the documentation sent out later. And with that, I'm ready for your questions. Thank you very much.
Many thanks, Per. Many thanks. That was quite amazing what gas turbines can do, also using biogenic fuels. There was one question from the audience, whether you have been already running gas turbines on syngas or on pyrolysis gas.
Yes, we have, let's say, within Siemens Energy, we have a gas turbine model program ranging from 5 megawatt up to plus 400 plus megawatts. And there are a few of the smaller units has actually been, let's say, developed. The combustion system have been modified in some cases to run on syngas, I would say. Yeah. It's very rare, but we have some examples, yes.
Right. Well, thank you very much. I do not see any further questions right now in the chat. So I think we're coming to the end of this webinar. As I mentioned in the beginning, we will have another webinar that will look on the role of biomass for supplying heat in a flexible way and why it will very likely play an important role in this context in the future. And I would like to thank all the participants for joining us. I hope you found it useful and hope to see you again in one of our coming webinars. As mentioned, this webinar will be online, and you will also receive an invite to our next events. Please also consider to become a member of the World Bioenergy Association. Thank you very much, and goodbye into the whole world.